Hi, my name is John and welcome to another edition of Statistics Quest. I'm going to pick up where I left off last time. We had been talking about a problem where we were pulling numbers out of a hat. And actually, I think I had left it on the board with different numbers, but basically, so I changed the numbers a little bit, and I had mentioned that I was going to go over something with different numbers. Well, these are different numbers. So, all right, so let's say we have 13 balls in a hat, okay? 6 are red and 7 are blue. And we're going to pull a ball 9 times with replacement. We want to find the probability of 3 red balls. Now, remember the idea of with replacement is actually, if you pull a ball and then you observe it, you put it back so that each time the probability is the same for pulling a red or a blue, okay? And we'll touch on that later as we go over something called the binomial distribution. But so we do need to put that, because if we weren't replacing it, it would, even though we could do the problem, it would not work out the way the binomial distribution would dictate. And again, we'll see that here in a second. So, okay, I'm going to do this problem actually the long way, so to speak, and then show you the short way, which is the binomial distribution. But it's important, and the reason I'm going to do it the long way is, quite frankly, for a couple reasons. One is just to show you how the binomial distribution is created, so to speak, how it's formed. And I think that's good because sometimes students get formulas and they're wondering, where did this come from? Well, we're going to try to piece that together, okay? The other thing is, and perhaps more importantly, is the nature of doing many probability problems is thinking through and multiplying. And so I'm going to emphasize that here. And it's really a good thought problem, and we'll see how this turns out. So, all right. So we're going to pull a ball 9 times, right? And we want to find the probability of 3 red balls. All right, I'm just going to make up any old example where we might have 3 reds and 6 blue. We'd have to have 6 blue, of course, if we had 3 red, right? So one such scenario would be we pull a blue, then a blue, then a red, then a blue, then a red, then a blue, 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 red, right? I just made that up, but we have 1, 2, 3 R's, 6 blues. That would be one way in which we could pull a ball 9 times and get 3 red balls, right? They're asking for 3 red balls. Okay. What's the probability of this? Well, every pulling a blue is 7/13, right? So we'd have 7/13 times 7/13. Why is it 7/13? Well, if we have a total of 13 balls and 6 are red and 7 are blue, so there's 7 out of 13. Similarly, red is a 6. Okay, so that's a 6, funny looking 6 there. Okay, and so each of the reds are going to be 6/13, each of the blues are going to be 7/13. If we multiply that out, we get that small decimal number. Okay, well, let's make up another example. All right, maybe we get 3 reds right off the bat, and then we get 6 blues. Okay, well, what's the probability of this happening? Notice what happens. So probability of a red is 6/13, 6/13, 6/13. Blue, 7/13. But what happens is we have 3 6s and 6 7s in the numerator, just like we did here. And we have 13s in the denominator. So we have the same numbers, only interchanged. And of course, if you multiply any combination of numbers and you switch the order of the numbers, you're still going to get the same number, right? Just like 4 times 2 equals 2 times 4. So same thing here. If we know we multiplied this out and we did this correctly, and we have the same 9 numbers, only in a different order, we get the same value there. All right. Now, I'm not going to go through all of the possibilities here, but we're going to talk through how you can determine how many possibilities, right? We looked at 2 so far, right? We can make up others. So we're going to ask the question, how many ways can we have 3 reds and 6 blues? Interestingly, this amounts to a combination problem. And again, let's think through this. It's not obvious, right? But, and this is one thing I always stress to my students with problems. I love these kind of problems. They're good thought problems, anytime you have probability problems. But so let's think through why it makes sense it's a combination problem, okay? Even though it's not explicitly given as a combination problem. An explicit combination problem would be something like you have, let's say you have 9 numbers in a hat, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And you're going to close your eyes, you're going to pull out any 3, and you wonder, how many ways can you get any 3 numbers out of 9 in a hat? That's a combination problem. It's 9C3. This plays out the same way, and here's why. And this is another thing I'll advise my students is write down scenarios. Scenarios kind of help, they help as a catalyst for your thought process. So what do we have here? We have red, I'm just going to focus on reds. We have reds in the 3rd, right? 1, 2, 3, 5th, and 9th position. Here we have reds in the 1st, 2nd, and 3rd position, right? Well, we might have reds in the 1st, 2nd, and 4th position, or 1st, 2nd, and 8th position, or 2nd, 5th, and 6th position, right? What am I really doing in trying to determine how many of these have? So think about what I said. We have reds in any 3 of the 9 positions. That is a combination problem. It is the combination of 9 things taken 3 at a time. And again, if you missed my last episode, we talked about combinations and permutations last time, so check that out if you need to. So what it comes down to is, quite simply, we have this many, 9C3. Okay, I'm not going to write them all out, right? Here's 2 of them. We have 9C3, and each time, what do we get? We get 7/13. We have 6 of them. That's right here. And we have 3 of the 6/13. That's right here. So it's a combination problem where we take this times this times this. All right, so I multiply this out. 9C3 is 9 factorial over 6 factorial times 3 factorial. Keep in mind, factorial is just taking that number multiplied down to 1. Now, here's another thing I like to do to keep your mind sharp, okay? I know our society is really kind of bent on calculators, and certainly calculators are needed, in many instances. But so what is this? 9 factorial is 9 down to 1, right? 9 times 8 times 7 down to 1, right? 6 factorial, 6 down to 1. So if we look at just 9 factorial and 6 factorial, if we were to write it out, wouldn't the 6, 5, 4, 3, 2, 1 from here divide out with the 6, 5, 4, 3, 2, 1 from here? So what are we left with? We're left with 9 times 8 times 7 over 3 factorial. That's actually what this is. And then so you have 9 times 8 times 7 over 3 times 2. That's 3 factorial. And then I just divide it out, right, the way we did back in 2nd grade. And guess what? We don't even need a calculator. Hopefully I did it right. I think I did. 3 times 4 is 12, times 7 is 84. So 84 is this 9C3. And so we have 9C3, which is 84 of these. Again, I would have been all day, but I could have written out all 84. We have this plus this plus this. So what is this plus this plus this added 84 times? It's just 84 times that. And we get 0.201294. So that's kind of the long way of doing the problem, okay? If you, and I wouldn't expect you to do it this way because you should get in the habit of recognizing something that lends itself to the binomial distribution, okay? I'm not encouraging you to do it the long way. I mean, if you don't recognize that it's the binomial distribution, then by all means reason it out. It ends up to be the binomial distribution. Okay, so you're probably thinking, what exactly is this binomial distribution? It's over here. Binomial distribution, we can write it out as the probability of R successes of n attempts where the probability of a success is P, okay, maybe it's 0.7, maybe it's 0.4, etc. Then the probability of R successes is equal to NCR times P to the R power over 1 minus P to the N minus R power. Okay, again, as I like to say many times, the bark is worse than the bite. This is actually a pretty easy formula. Now, if we go back to this problem, okay, what do we really have? So let's just say I ask the question, or you're posed with the question, what's the probability of getting 3 red balls out of 9 attempts, okay, given these assumptions? Here's what you would do. You would say, oh, okay, we have 9 attempts, right, because we're pulling 9 balls. We're calling a red a success, and it doesn't matter what you call a success. You'd see that it would work out the same way if you did it in terms of blues, but we're just going to do it in terms of reds. So you have n equals 9, r is 3, because we want 3 successes if we're defining a red as a success. What's p? P is the probability of a success. That's the probability of a red. What is the probability of a red? It's 6 out of 13. What is 1 minus p? Well, if p is 6/13, 1 minus p must be 1 minus 6/13, which is 7/13. So what do we have here? We have 9c3 6/13 to the 3rd power, 7/13 to the 6th power. That is exactly what we have here. Okay, so again, these are actually pretty easy problems. We're going to go over another, but these are the components of the binomial distribution. So very often we see problems that lend themselves to binomial distribution, especially when you're flipping a coin, right? Flipping a coin is an easy example. For example, you could say, well, if you flip a coin 10 times, what's the probability of getting exactly 7 heads? Binomial distribution, plug in numbers, okay? I'm going to go over one more problem, and so if you didn't follow this, you will see how easy this really is, okay? Let's say we're playing a game, okay? In fact, I'm going to play a game tonight we have game night with my lovely wife and 2 friends, so we're going to have a total of 4 people, okay? And let's just say we play 5 times. I'm not sure what the game is, how long it takes, but let's just say we play 5 times, and somebody wins 3 games. Okay? Well, it seems, not so easy, right? I mean, if you have 4 people, and let's just say everybody has the same chance of winning. All right, and so somebody wins 3 games, and they're kind of patting themselves on the back, and they say, oh, I wonder what the probability of winning 3 games is. All right, well, what they're really asking is, what's the probability of winning at least 3 games? And that's a different question, okay? And in fact, I mentioned this in an earlier episode. We were talking about flipping coins. But so they win 3 games. Say, oh, I wonder what the probability that I won at least 3 games. So we're going to pose it this way. Probability of winning at least 3 games, well, that's either winning 3 or winning 4 or winning 5, isn't it? Right? At least 3 is 3 or 4 or 5 because you're playing 5 times. So we're actually going to use the binomial 3 times, okay? So you'll get in the habit of doing that, and we're going to add them up. So let's first say we ask the probability of winning exactly 3. And if you understand this, you should understand basically everything that I've gone over in this session. And again, it's pretty easy. Okay. 3 wins. So we're going to call a win a success, right? 5 games. So it's really 3 successes out of 5 attempts. That's right there. It's 5C3. The combination of 5 attempts with 3 successes. Now, what's the probability of a success? That's easy. If you assume that everybody has the same ability and they have a 1 out of 4 chance, right? There's 4 people. That's just 25% or 0.25. It's 0.25 to the 3rd power. What is this power? It's r. That's the number of successes. Okay, and then the rest of it is, well, the probability of 1 minus p is actually 0.75, right? So look at it this way. If 0.25 is a success, the 1 minus p is actually a failure. Well, if 25% of the chance you're winning, 75% of the time you're losing. And you raise that to the 2nd power, n minus r, so that's 5 minus 3. And you multiply it out as you get 0.088. Before finishing this, let's even break it down. Sometimes here's the kind of the easy way to remember this formula. Okay, it's combination of 5 things taken 3 at a time. And then what I'll advise my students is, in words, it's the probability of a success to the number of successes times the probability of a failure to the number of failures. So that's kind of a check, isn't it? If you make sure your exponents match up with the corresponding probability. So again, probability of a success raised to the number of successes, probability of a failure raised to the number of failures, 0.088. If you understood this one, you should understand the other two. They work exactly the same way. So we ask, what's the probability of exactly 4 wins? Well, that's 5C4. You're taking 4 wins, or 4 successes out of 5 attempts. 0.25 to the 4th, 0.75 to the 1st, works the same fashion. Here we want 4 successes, probability of success 0.25, right? 0.75 is the probability of a failure raised to the first power. So we multiply this all together. Again, I did some behind the scenes work. 5C3, you know how to do that. 5C4, right? That's just the combination formula. So, okay, we get 0.015. Probability of 5 works the same way. We get a very small, right? That's really tough. If you win all 5, wow, 0.001. So the probability of 3 or 4 or 5 is to add them all up. If we do that, we get 0.104, which is about 10%. So again, the probability of winning at least 3 is 3 or 4 or 5. Add them up, you get approximately 10%. That's the binomial distribution. Many other examples. Anyway, so if you do still have questions on it and you want to ask about it, I'll even write out another one in the comments if you need to see another one. But hopefully this helps you understand the binomial distribution. So again, if you haven't liked or subscribed, please do so. Feel free to make any comments, and I will see you next time on Statistics Quest.